Hello, my name is Ivan, and I'm going to tell you about gravitational signals from superconducting cosmic strings. The work was done in collaboration with Laura Souza, and it's available now on arXiv with the following number. Early stage of the universe is characterized by very high energy scale, which is not accessible on a terrestrial laboratory experiments, and it will be really desirable to access this high energy with some observational data and to understand how actually we can expand our standard model of particle physics to the very high energy scale. And one particular phenomena that can help us to do it are the cosmic strings. In particular, once they are created in the very early universe, they can persist up to the present time, and moreover, they should leave very distinctive observational feature by which we can understand better the high energy physics. First of all, what is the cosmic string? It can be considered as the localized field configuration that is stable due to topology of the vacuum manifold. In a more simple manner, it should look like a linear concentration of the energy with a very small width. For instance, the cosmic strings that are created on a gas scale, the width can be the size of the proton. However, the length of the string can cross the whole observable universe. And in that sense, we can say that this is like a one-dimensional object, almost like a string, with a very big concentration of the energy. For the more details, we can consider a particular example of the abelian-Higgs model with U1 symmetry. Here we have a complex scalar field phi, which is minimally coupled to the gauge vector field A, and with the following Lagrangian and the potential that has the following form. One can observe that this action is symmetric under local U1 transformations. If we apply this transformation for the action, it will be invariant. However, the vacuum state or the minimum energy configuration, which is denoted here by the circle, by dashed line, they are not symmetric. Each of these vacuum states, like 1, 2, 3, 4, they're all different. In that sense, for the vacuum state, the symmetry is broken. And this particular model can give rise to the cosmic strings by describing, well, now what's considered the Kibble mechanism. In the very early universe, when the energy is very high of the processes, the symmetry U1 is preserved. However, as the universe expands and cools down, the symmetry will be broken, and the field will choose one of the vacuum. Here we denote 1, 2, 3, 4. And in a real space, if we consider different point of the consideration, like 1.1 and 3, for instance, that are not correlated between each other, there is no reason why they should choose the same vacuum. And if we create a loop in a space, we consider the loop in a space where the field fell into the minimum in such a way that they create non-trivial widening around this hilltop, then in the middle there should be a string, as it's demonstrated here. 1, 2, 3, 4 is the point around the string, which is I in the vacuum. And the string itself is the trap on this top of potential concentration of energy that is represented by the cosmic strings. In the early universe, we anticipate the production of many of them. And to understand their evolution, one can appeal to the simulations. Here, an example of this abelian-Higgs U1 model with a critical coupling. And that's how they look like. However, we don't have a really U1 symmetry in our standard model description of particle physics, and to some extension, they include a lot of other fields that can interact with each other. And here an example of the SO10 symmetry breaking chain, where in the end, in the final, when we reach the standard model, the strings should be produced. And there are many other scenarios, like supersymmetric grand unified theories, or the dynamical generation of the right-handed neutrino masses, or even QCD fluxes. All of these scenarios, they can give rise to the cosmic strings. And by studying constrained cosmic string, we can actually constrain these particular models of the high energy physics. What is more important, that as I said, we don't see here explicitly U1 symmetry. We actually see a lot of different fields that interact with each other. And the question, is this time model really applicable to the realistic scenario? Well, if we try to include the interaction with other fields, then we should consider the generation of the current on the cosmic strings or superconducting cosmic strings. There are several mechanisms that can give rise to the current, such as the coupling with other fields, as I said. The fermion can be trapped on the cosmic string core, or the vector flux. Non-abelian cosmic string give rise to the current. And for instance, the very often used in the popular literature axion types of the cosmic strings, they also should be superconducting. And that's why abelian Higgs model maybe doesn't always represent the realistic scenario. We should try to make everything, of course, as simple as possible, but maybe not simpler. And if the current can change our observational outcomes, we should take into account. One way, of course, is try to make the lattice simulation, similarly as I was demonstrating for the U1, symmetry example for the abelian Higgs field. However, here the situation is much more complicated, and to achieve a really good simulation for this field theory evolution is quite complicated task. However, here are some progress in the recent results. Since we're quite limited by the simulations, we tried to approach this problem through the effective consideration. We use the developments that was carried out a lot by the Brandon Carter, and we use effective description of the cosmic strings. In particular, this part is the Nambu-Goto, is just an infinitely thin cosmic string, like the first order approximation, and the current is modeled by the master function. There is a function that depends on the current kappa, and this master function defines property of the string that should mimic original field theory model. Additionally, of course, we have external vector field and the coupling between this external vector field and the current on the cosmic string. Here, I would like to notice that the current kappa has the chiral limit, which is called. It means kappa goes to 0, but it doesn't mean that the current by itself is 0. It just means that the current by itself is the light-like vector. Okay, when we add the vector component, we open another channel of the massless radiation. For the usual string, we have only gravitational radiation, but here for the first time, we consider also the vector field radiation. Please look at the paper here. Here we studied the gravitational radiation for the current carrying cosmic string without the channel to the vector field. And now we apply the all developed formalism for the vector field. And in particular, we studied two types of loops, burden types of loops and loops with kinks, which has a particular features of radiation, and which are the most typical one that we anticipate. And in particular, we try to understand how the radiation efficiency behaves in these cases. Here, the first type is the burden types of the loop. It should contain cusps. Cusp is the point on the cosmic string. This is like this sharp point of the red cosmic string. And this very sharp point where the curvature diverge should move with the speed of light for Nambu-Goto case. However, if we include the current, in general, the cosmic string will be smoothed out, and it will have the shape something like this. It's possible to fine-tune the current in such a way that we reproduce the shape of Nambu-Goto string. However, the point of the cusp will not be moving with the speed of light. It will have subluminal velocity. And as we studied, the radiation for this case, the vector radiation, is exponentially suppressed. This is the spectrum of the vector radiation. And we see the exponential suppression for this case. Similarly, as it was found before for the gravitational radiation, if we include the current, the presence of the current. However, here we consider the vector radiation in addition to the gravitational one. As well, we did the study for the loops with the kinks. Kings is the point of discontinuity of the tangent vector along the string. This is also the point that for the Nambu-Goto case should move with the speed of light. However, when the current is present, this point will be moving only with the subluminal velocity. However, what is important, the radiation in that case will have a power law, and it will not be exponentially suppressed. And here we see for the vector radiation, it has a power law. And what is interesting, it's similar as for the gravitational radiation. For the Kings, we have a power law decay in the spectrum, while for the something that's supposed to be like a cusp, we have an exponential suppression. Okay, we studied two particular features, Kings and cusps, and then we averaged over possible shapes of these burden loops and King's loop, and we found the average radiation efficiency for these cases, for these loops. And we studied two particular cases. One is the chiral types of the loops, where the current is light-like, and the symmetric. Symmetric when we tune the current in such a way that we reproduce Nambu-Goto shape. And this is two of the most extreme cases, and all of other cases following between. And what we found when we studied the burden loops and the King's loops, the dependency of radiation efficiency depends on the current in a similar way. Here we put a plot for the G, which is related with the current by the following set of expressions. And we have two particular limits, as one can see. One limit when G plus minus equal to 1, which corresponds that there is no any presence of the current. And this is this point. And of course, there is no radiation. And this point corresponds to Nambu-Goto case. Another point where G plus minus equals 0, this is the Wharton case, the stable configuration of the loop which stops moving and is stopped radiating. Okay, we understood how the radiation efficiency behave. Now we can study how the loop decay by itself. We write equation for the loop length, L, and also we write equation for the charge. And here, as you can see, there are two channels, one for the gravitational emission, another for the vector emission. The vector emission is included for the first time. Before, we only studied with the gravitational emission. In addition, there is a possibility of the charge leakage. Charge, because of quantum mechanical reasons, can escape the loop. And as a result, there will be a decrease of the charge. That was anticipated in generally for the cosmic strings. However, it's interesting to also look on the scenario for the formation of the Whartons. In that case, the leakage is absent. There is no leakage at all. And if we start with any charge, it will saturate to the maximum value. And in the end, we'll get some configuration of the loop that is stable, at some size of the loop that stops decaying. Another more realistic scenario is when the leakage function is present, and of course there is some escape of the charge. And in that case, we found a scaling solution for the charge. It means that independently from which charge we start initially from the loop, it will eventually scale to some constant value. And in that case, loop can smoothly shrink and eventually decay. This particular scenario of the loop decay will be applying for the prediction of stochastic gravitational wave background. But in addition, we need to include the model by which we will model our string network. And this is the charge velocity dependent one scale model, which was developed in a set of publications. And it's also based on an effective description. And through this effective description, we average parameters through the whole network. And we obtain the string core energy, the bare energy, full energy, together with the current. And the main parameters, thermodynamical variables that we are going to use is the velocity, the RMS velocity, the average velocity of the string network, characteristic length, which is inverse proportional to the string density, which means that as the bigger characteristic length, as smaller the density. We have also the charge and the chirality. Chirality can be a negative or positive value, and it depends in which direction the current propagates. In average, we assume that chirality should be 0 because on a big network, there is equal possibility to propagate for the current to be time-like or space-like vector. As a result, we're left with the three variables, and as it was demonstrated in this publication, there is a scaling regime when the velocity goes to RMS velocity goes to constant, charge goes to constant, and characteristic length goes proportional to the time, which is similar to the usual scaling on the standard cosmic strings. Okay, now we have all ingredients, and we make our prediction for stochastic gravitational wave background. First of all, we can notice that variation of the coupling of the string with the vector field can influence and can suppress the stochastic gravitational wave background a lot. If we start to increase our coupling, it's clearly that there is additional to the gravitational emission, there's additional channel of the vector emission. And as the loop decay, the more radiation goes to the vector channel and less goes to stochastic gravitational wave background. And here, the suppression, like changing the coupling variable for 5 orders of magnitude, gives a suppression for around 12 orders of the magnitude for stochastic gravitational wave background. Also, we vary the amount of the charge, and here the dotted line corresponds to the Nabu-Goto case, and the different value of the charge corresponds here. As we start to increase the charge initially, the amplitude starts to decrease. It corresponds to the fact that the string network actually become less dense, and there is less radiation. However, later, as the charge increased more and more, the stochastic gravitational wave background amplitude started to increase. It's mostly related that the radiation efficiency decreased so much that the loop that should have decayed long time ago, they decayed more closer to our redshift. And all the radiation that they emit, it's not redshifted, but it's emitted recently to us. And as a result, the stochastic gravitational wave background amplitude starts to increase again. And that's what we see here, the dependence on the stochastic gravitational wave backgrounds on the amplitude of the charge. And we decided to look how this configuration of the cosmic strings, superconducting cosmic string, how it can change our interpretation of the data of pulsar timing array. And we demonstrated that if we choose some fine-tuned charge, which is very high, very close to saturated case, we can even reach 1 sigma of the pulsar timing array. We can be inside of this 1 sigma. However, of course, such a very high charge will violate other constraints of the cosmic string, such as CMB and other prop of the gravitational waves observations. But here we found one particular example, which is in 3 sigma deviation, which stays in agreement with all possible other constraints. And here we demonstrate these parameters. This is the closest one as we could come to the pulsar timing array result. But there are a lot of other effects that should be investigated, and we leave further and more detailed investigation of these aspects for further work. As a result, I want to conclude and to give you 3 main messages. First of all, current on the string are crucial if we want to restrict our high energy model physics. And also it gives us a sense which kind of coupling, if we in one day we detect cosmic string, we can really understand which kind of couplings between different fundamental fields was on this time. Also, the vector radiation can significantly suppress stochastic gravitational wave background, as we see. However, it can potentially reconcile with PTA. And upcoming gravitational wave mission require a deeper understanding of possible sources and potential deviation from standard Nabu-Goto strings. And that's why we need to put more efforts to study these particular types of the string. Thank you for your attention. And if you would like to see more details, please visit our preprint